We'll do summarization in the maxima-minima as we have covered all the topics till the kind of finding the critical point when we have a constrained region. So that's what is the idea. So before that, we'll take some examples. So before that, we will take some kind of examples, and then we will see that how things goes as far as examples are concerned. Maxima and minima, if you see kind of anything in your in the mathematics, anything in the mathematics, okay, probably it will be like it has people consider that mathematics is something that is that is theory. Mathematics is something that is theory. So the practical is the commercial subjects that we should understand. But mathematics is not only theory, it is full commercialization. So when we talk about the extrema point, the critical point, maximum, minimum, then it is directly attached to profitability. If I have considered that what is the profitability of a company? A company which produce an item and sells the item in the market, then what is the profitability? Profitability is how much it earned, how much is the revenue collection that happened through the market minus what is the production cost. Revenue minus cost equal to profit. Now, suppose that somehow the company is able to make a equation, algebraic equation. Company is able to draw an algebraic equation to deduce an algebraic equation where profit is an algebraic equation, profit is dependent component, profit is the end result, where the independent component are like raw material. Okay, so profit is nothing but production for production, the kind of the net income means revenue that is generated while selling the item in the market, revenue minus production cost. Okay, so he can go differently like production cost. Production cost, if we see, then production cost is dependent upon labor cost. Production cost is dependent upon the, if investment is done, all the machines are purchased, then day by day what company is investing is the labor cost, and the raw material it is produced purchasing to make the production. So raw material are being purchased day by day basis, and labor costs are being given day by day basis. So this is the main expenditure as far as production cost is concerned. If company is able to deduce a algebraic equation, an algebraic equation that is dependent upon algebraic production cost is dependent upon independent variable like labor cost. Labor cost has some variable, and then all the raw material is variable. This raw material, how many numbers? The raw material, how many numbers? Then the total cost of the production is dependent upon labor cost, this raw material, in what fashion? Exponential of this raw material, or a square of this raw material, or 600 minus 0.3 into this raw material count. So if someone makes the full kind of algebraic equation based upon these three independent components, okay, two raw material and one labor cost, or if I remove the labor cost which is not variable, then all the raw material, because production, if I make a produce, if I generate the production, then the produce what you make, then cannot be straightforward dependent upon all the material. It would be more dependent on certain raw material, it would be less dependent upon certain raw material. So production cost equal to like 600 minus 0.3 P. P is one raw material, Q is one raw material, like this. Then the production cost we can reduce as a kind of sum equation in P and Q. Now production cost, if I want to do the minimum, then I have to do the derivative of production cost. Suppose there are two raw materials that are being used, P and Q. P is nothing but one type of raw material and P is the count of the raw material. So if I am using a raw material 1 and then its count is P, P number of that raw material that I am using. And I have another raw material that is another raw. So there are two raw materials. Suppose one is iron and one is tungsten. I mean, someone is making bulb. So then kind of tungsten or whatever the material is, and then glass item. Okay, bulb it is making. Then how many kilogram of the glass has been purchased and how many kilogram of the tungsten has been purchased. Now the production cost is how it is dependent upon the how many kg glass is used and how many kg of tungsten is used. So then later we can see that if I have used P kg of iron and Q kg of tungsten, then if iron is kind of some amount that is per kg and tungsten is some amount per kg, then P into something plus Q into something is the total cost. But the production when it happens, then how production as such as the quantity of the item, how it is dependent as far the algebraic equation is concerned. Okay, so like when I produce a kind of bulb, then it is like if P is the kg of the glass, then P to the power 2 by 3 and Q is the tungsten, then QT to power 1 by 3. This is how it is dependent. Means I can say the production production uh, production of the item produced is dependent like P to the power 2 by 3 and Q to the power 2 by 3. Means if I increase P, okay, the kg in glass, then production would increase more. If I increase Q, then production would increase not that much. So it is more dependent upon the quantity of the P rather than Q. So like this, if I get the equation of production cost based upon some independent variable, then I can do the partial derivative for the P and partial derivative the Q. And if I set it to 0, then I can find the minimum production cost based upon the certain P and Q value. So that much only I'll use and I'll make the production cost minimum. Revenue, same thing I can do. Now if I subtract revenue to the production cost, then I can, if production cost is minimum and revenue is also is a algebraic equation based upon sub item and revenue I make it maximum. Revenue, company is making revenue by selling the produce in the market. When it is selling the produce in the market, while selling it, the selling it again, it can think about what are the independent variable on which the revenue is dependent upon. Like if I do the production, then production is dependent upon two items, glass and tungsten. This is what we are saying. Okay, and then similarly when I'm making the revenue, I'm selling the item in the market, then it is dependent upon which all other factors. Okay, it can be dependent upon kind of the market condition, what it is, the kind of demand in the market, then how many items we carry. If we carry too many items, push too many items in the market, then net profit may decrease because demand would decrease. So based upon all the things, the revenue we can have algebraic equation. Now if I have three independent components, based upon the three independent components, we will deduce the three partial derivatives and we'll set it to 0, and all three independent components we will get at which it will have extreme or critical point. Income is dependent component dependent upon three independent components, and if I derive the income, if I do the derivative of income, differentiation of the income based upon all three items separately called partial derivative, and I set all these partial derivative to zero, then I have value of all three components, different set of value for all three independent components. Now I'll place in the algebraic equation, I'll find at what value of all three independent component ABC, if it is ABC, then the profit is maximum. So this way I can have the maximum profit. Now production cost, I have again like in P and Q I said, so I'll set a P and Q so that production cost would be minimum. That is the idea. Production can be maximum, but production cost, that is the main idea. Production cost should be minimum. Now I'll get a value of P and Q at which production cost is minimum. So production cost is an algebraic equation where independent components are P and Q. Then production cost, I'll do the derivative, partial derivative with P and Q, set it to zero and get the value of P and Q, set in the algebraic equation and check where it is minimum. If that is the case, take work. Then now you got the minimum production cost, maximum revenue. Then if you do the subtraction, you get the maximum profit. Now whatever the independent component that is in the production cost, that you have to use that much only, so that production cost would be minimum. Revenue, whatever the independent component are, you select the amount and the scenario is selected in such a fashion, because you know the numbers now through the partial derivatives, and then coming to maxima, and then your revenue is maximum. Revenue maximum, production cost minimum, then profit is maximum. So I would say the most high class commercialization, the most high class management, people do kind of MBA and those kind of things to come up with the company policy as far as the business is concerned, where profitability is concerned. I believe that mathematics and especially calculus is the best way to dig into it, so that the maximization in the profitability can be achieved in the company, rather than going for MBA and this kind of thing, which is does not make. That's why companies, many companies, they come to loss because of heavy expenditure in these kind of jobs. If you go for MBA kind of job, you have to give tons of salary, and then they don't know anything. Only thing what they know is how to go to the customer and start polishing the customer. If you see the MBA degree, what they do means they will be read on the employee of the company, so that the production cost should be less. This is the way they do. They show red eye to the employee, so that no one would demand high salary or something like that. So production cost will be minimum. And then when they go to the customer, at those places they behave like beggars, they behave like slaves in front of the customer, so that they would buy. This is MBA. Now production cost is less, revenue is high, so profitability is high. Certainly profitability will be high, but for some time, because customer at the end, he wants the quality in the production. He does not want your sweet voices. Sweet voice would work, but for some amount of time only. Beyond that, the actual production quality and how it is meeting the time, when customer demands, then on time it should reach to the customer, and then the quality of the product should be very high. Then only it will go long race horses. It is called long race horses, where the kind of long relationship with the customer is only possible through the high quality of the product. So high quality of the product will come when you have top class mathematical equations looking at all the scenarios, and then you have maximization, minimization in all the equation, and then you have completely set up the kind of all the possible independent variable values, and you stick to those values. If you now found that you have 10 steps in the reaching to the market, when from the buying of the kind of from research to buying of the raw material, producing it, and then preparing and then going to the market. If you have different steps, with all the steps, whatever the independent component value you feel that those steps would do best, then those independent variable just keep in the registry that these are the value in this scenario. There the things are best. Just make it happen, and then you have a full chain that is automated, and then it goes to the market with high quality product on particular on certain time that customer is expecting, and you have long race horse, long term profitability. Okay, headache is less because you are not doing anything. Mathematics is doing everything. You invested in one go. Don't much invest in time, invest in mathematics. Means at the beginning you invest heavily in the mathematics, in the sense that you come out of the formula. This is what the artificial intelligence and machine learning they are doing nowadays. You put time and money in generating the formula. There it is called model. So model means a kind of you go with a kind of labeling or unlabeled, supervised, unsupervised learning. So they distribute in that fashion, and then you put some time at the beginning and money in coming out of the mathematical equation. What will happen tomorrow? If you have all set of mathematical equation, that is called model, either it is supervised or unsupervised learning, and then whatever situation you are getting at runtime, just it would match with all the formulas, and it will go along the way it should be, and then you have top class production, and that is confined into high high precision of time, high precision in the quality, high precision in the time, and then time to the market is perfect. Okay, if anything is changing at the runtime, your mathematical equation would take care because you have invested in them. So don't invest in MBA and this kind of crap degree, because what those people will do, they don't know anything but to either show the red eye or a smiling face. Other than that, certainly, that's why these technologies are coming up, because people have seen it that this does not work. The only the degree or only entity that would probably help you at the runtime is mathematics. So heavy calculus, heavy vector mathematics, both are heavily being used in artificial intelligence and machine learning. Machine learning is nothing but it's a kind of mathematics of calculus and vector, nothing more than that. So it's a top class idea to kind of be very do best in the minimization and maximization. That's why we have series of videos in minimization and maximization, so that you can now have the profitability of your company as maximized. That is the concept. Anyway, now we will see that what we have done, and then finally we will take few examples. So minimization, maximization, we covered in two sections. One is one independent component, that is X, and one is multivariable component, that is X and Y. So first is Fx, that is y equal to Fx, that is independent component is x1, and another is z equal to fxy, and that has independent component is x and y. So if independent component is x, then there is only x axis, and whatever the dependent component we are getting, that is vertical, that is y axis. Y axis is the result where the input to the function which generates the result, that is the function fx, is x-axis value. If I set x-axis value, then pass that value to fx, it generates the y. This is what we saw. If I connect all the y, then it is a curve. Curve can be minimum. If there are so many minimum in the curve, then we call it local minima. So many local minima. If there are so many maxima, then it is called local maxima. Out of all the minimum, whatever we see the max, the lowest point, that is the global minima. Out of all the maxima, whatever we see the highest point, we call it global maxima. So this is what we saw. How we get the local minima and local maxima is we set dy by dx to 0. If y equal to fx, then dy by dx I get as algebraic equation and set it to 0. Whatever set of x value we are getting, at those x value, it is either local minima or local maxima. We call it extreme point. Now, I can go with dual derivative again to find it is maxima or minima, or I can take those fx values and check what is the fx value. And then out of that, I get the global minima and I get the global maxima, or all the local extreme points what we have got, those are minima or maxima. Those things we can get. Either we set it to the fx and get the value, or through d2y by dx square double differentiation, I check all the points what we have got as local extrema or local minima or local maxima. If double derivative is negative, then it is maxima. If it is positive, then it is minimum. Okay, then we saw that in a kind of double independent variable x and y. So z equal to fxy. If z equal to fxy, then I have dz by dx and dz by dy, xz plane and yz plane. So xz plane will come as curve only and yz plane will come as curve only. So dz by dx I set to 0 and find, then I will have kind of one condition, dz by dy, whatever comes algebraic equation, I set it to 0. Now both equation we try to find out set of xy values where it is kind of local extrema. So three dimensional where two independent variable are there, then we have xy independent component. Xy is a xy plane. Xy is a xy plane. If it is a xy plane, then against each xy point there is a vertical value, that is fxy, that is z. If I connect all the vertical points, then it leads to a surface. If it is a surface, then it will have local maxima and local minima, so many. Then whatever so many are, that so many x comma y point I'll get, and those x comma y point we have fxy, that is local or local minima or maximum extreme point. Now I can check again the fxy that they are maxima or minima. If I get all the maxima, local maxima and local minima, then whichever is the minimum is the global minima, whichever is the maximum is global maximum, or we can calculate the double derivative. Here it is the fix. Here is the problem. In single dimensional, we saw that taking the double derivative d2y by dx square solves the problem as far as finding the minima or maxima is concerned. Whereas here we have two variables, x and y. So if I take double derivative, then there are three double derivatives, d2z by dx square, d2z by dy square, and d by dy of dz by dx. So one is called fxx, one is called fyy, then another is called fxy. There are three partial derivatives here possible as far as double derivative is concerned. Now, how we have to mix all three so that quickly I can say that whatever the local extrema we have got, either it is either maxima or minima. For that, we came to a very high class fundamental, that how to turn a function into a polynomial function. If I have a function fx, fxy is a full-fledged function, then how I can write another function called gxy, which is only polynomial. Okay, x to the power 0, y to the power 0, x to the power 1, y to the power 1, x into y, then x to the power 2, y to the power 2, x square y x square, x y square. In that fashion, if I keep going, this is set of polynomial with all set of degree. So if I have fxy function, how I can get a gxy, that is complete polynomial. So I call gxy as polynomial approximation of fxy, where fxy may not be a polynomial or mixture of polynomial and logarithmic and other. So if I get gxy, Then dxy, if I go up to 2 degree only, 3 degree onwards, if I scrap it, then the first degree, that is dz by dx. So we saw that it comes as fx x plus fxy plus fxx into x square by 2 plus fxy xy plus fyy into y square by 2. So fx x f plus fyy, so dz by dx and dz by dy, they are anyway 0. So it comes to completely a quadratic equation. Now quadratic equation we match to another equation, that is ax square plus bxy plus cy square. And then we saw that we came to a kind of a concept where I have a and b as 4ac minus b square. Two terms we saw, and now based upon these two terms value, now we came to a conclusion that whatever xy point we have got as local and local maxima and local minima, the local extremas, whatever the point I have got, setting dz by dx is equal to 0 and dz by dy equal to 0, whatever set of xy point, those are local extrema. Now based upon this quadratic equation, what we got through gxy, that is polynomial approximation of fxy, the at this point it is global, it is local maxima or local minima. So that we can get, look, setting this quadratic equation in a form of ax square plus bxy plus cy square. Now, so this is what we saw. So at the end, through double differentiation in the multivariable case also, we could find that these particular points where the local extrema or local critical point exists, these critical points are maximum or minimum. So this is what we saw. Okay, then we proceeded in a kind of constraint maxima or minima. So when we came up with the gxy formula, then in gxy formula, when we deduce the polynomial approximation of fxy as gxy, then we saw our equation also. So we deduce the multivariable integral by part. This is the way that for the single independent variable fx and gx approximation of fx, that we achieved by integration by part. Now for the multivariable case, that we kind of generalize in a multivariable case. How generalization can happen, that was our kind of research. So that we are going to file as disclosure. Okay. So become part of it. This is what I would kind of invite people. You can become part of it. So that is kind of disclosure we will file, that how in the multivariable case we can have polynomial approximation of any function. Whatever is available right now, that is too difficult and difficult to understand. Probably not much clear explanation has been provided. But only thing is that result is ready. Okay, now then we come to a situation where if I have a function, if I have a multivariable function, then it is a surface. Now surface has so many local minima and so many local minima and local maxima. So it is called unconstrained calculation, because when we take xy point, if I have a surface, for each surface point I have z value. Against each z value, I have down the line independent variable through which this z value or fxy has been generated. Those independent variable x and y, they lie on a surface, that is called xy plane. If this is x-axis and this is y-axis, then this is fxy, that is vertical, or z. Against each point xy on the xy plane, I have a particular fxy or z value. If I connect all those, it becomes a surface. Now surface is like this, like a mountain where there is a hill, and then again there is a kind of valley, then hill, valley, like that. So if that is the case, then how many peaks are there? That is called local maxima. And how many ditches or valleys are there? That is called local minima. Out of them, one global maxima would exist and one global minima would exist. But this is calculated on full stretch of xy plane. This is called unconstrained region. If I make it constrained in the sense that xy I had taken minus infinity to plus infinity, both x and y. Now I have to choose x and y in a way that it will be below or on the line that is called x plus y less than equal to 3. This is what we saw. If I have a line x plus y less than equal to 3, if I draw a line on the xy plane, now x and y value that has to be chosen now, that will be below it, x plus y less than equal to 3 or equal to 3. On that line also it can be chosen, but it cannot be more than 3. Now this is the constraint. Now idea is, if I have fxy and then I have another equation that is called gxy, and gxy is the constrained algebraic equation for the fxy. Now in those constraints, what is the global maxima? Global maxima is full minus infinity to plus infinity. Global maxima means if I have a constraint, inside the constraint, if I place a constraint, then constraint is the universe. Other places we forget completely. So whatever the constraint I put inside the constraint, now I have to see what is the global maxima and global minima. What are the local minima and local maxima? That is the world now. So in the constrained region, we also call it closed region, bounded region, unbounded region. That also we saw. So if it is 2D, then we have to take interval. So closed interval, bounded interval, unbounded interval. Now if I take 3D, where the independent component is a surface, then we have closed region, bounded region and unbounded region. That also we saw. Now if I have a function fxy, then this function should have extreme point only in particular closed region. Okay. So if I say x plus y less than equal to 3, I draw a line, and below the line or on the line, that is a closed region now. So x, y, we have to take value in that region only. Now there is a Lagrange way through which we can kind of calculate the x, y points at which it attains the maxima or minima value as far as constraint is concerned. And then we check against the fxy, these are the minima or maxima. And we come up saying that we have calculated minima or maxima based upon the constraint. This is what the Lagrange says, but we have our own mathematics. Okay, so this is what we saw. So probably we will discuss little bit about it, the Lagrange way and our way, so that it will be kind of more clear, and we will complete with this one. So Lagrange way, if I have fxy and there is gxy, so gxy, suppose it is x plus y less than equal to 3. If that is the case, then Lagrange say that what we are trying to do, we are trying to find the maximum f value. If I try to find maximum value of f, this is the requirement. Maximum value of f, then I have to know the value of x comma y. At what x and y I achieve maximum value of f when I satisfy the constant x plus y less than equal to 3. So x plus y less than equal to 3, if I have set of x and y points, in those points, what is the point at which f is maximum? So now he is talking about taking different contours. F, I'll take one value, next value, next value, next value. If I have f equal to a particular value, then against that particular value, I have set of xy points. Certainly, if I have fxy equal to x to the power 2 by 3 and y to the power 1 by 3, if I take f as a one particular value, then I'll get set of xy point through which I'll get this particular constant f value. So a particular f value, I have set of xy point. So that f value is called contour. So at that particular contour, now on the xy plane, then I connect all the xy point that satisfy this contour value or z value or fxy value. Like that, I keep increasing the f and I draw the line. till it touches the x plus y less than equal to 3, because I have to increase the f, so the f would become maximum. That is the idea. Now when f is maximum, then it would just touch the x plus y less than equal to 3, or the constant gxy. If I grow fxy little more, then it will cross the line. So at that point, if you see, then fxy and gxy, that is the constant line, they touch each other. When they touch each other, then gxy is the tangent at of the fxy. At that, if they touch each other at the point called x0, y0, or set of points, they touch each other. I am saying they touch each other at one point. Let's think about it. So if say they touch each other at one point x0, y0, then at x0, y0, fxy and gxy, that is the constant line, gxy is x plus y less than equal to 3. So constant line is x plus y equal to 3. Whereas fxy is x to the power 2 by 3, y to the power 1 by 3. If I draw fxy for a particular set of xy, y, where I know that what is f, for that f, if I draw the contour and then x plus y, if they touch each other at x0, y0, then x plus y equal to 3 is tangent. So it is tangent at x0, y0 point to the fxy. This is what he saw. Now if it is tangent, then gradient vector of fxy at x0, y0 is radial, means perpendicular to the fxy at that point, and gradient to gxy, that is x plus y equal to 3, both gradient are perpendicular to their function. If that is the case, then if this is the line, then this is gradient. If this is the line curve, then this is the gradient. Both are parallel to each other. They are perpendicular to their curve, but now they are parallel to each other. If that is the case, then if gradient is nothing but it's a vector. So gradient vector, if they are parallel to each other, then they only vary in the magnitude. So we can say gradient of fxy equal to lambda gradient of gxy. So fxy, gradient of fxy is a vector, gradient of gxy is a vector. So both are in same direction. So I can say gradient of fxy equal to gradient of gxy. But since magnitude varies, so I can say lambda into gradient of gxy. Now fxy, gradient of fxy means it's a vector, it has x component and y component. So fxy I'll differentiate with the x and y, and I get the gradient of f. Similarly gxy I'll differentiate with x and y, I get gradient vector for the g. So f and g, if I get gradient vector, then lambda. So if I see the gxy, that is x plus y equal to 3, then gradient vector is I plus j. Whereas if fxy is x to the power 2 by 3 into y to the power 1 by 3, then gradient vector is 2 by 3 into x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3 j equal to lambda and braces I plus j. Now for lambda, if I say lambda equal to this x component and y component, now whatever I have on the left side equal to lambda I plus lambda j. So lambda equal to some x component here. So lambda equal to 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3. Again lambda equal to 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3. Now if I equate these two, I get relationship between x and y. Typically it is x equal to 2y. This is what we got. Now if I place in the equation x plus y equal to 3, I get y equal to 1 and x equal to 2. Now when x equal to 2 and y equal to 1, at that point the maximum f can be achieved where it touches the gxy. This is what we saw. Now if I place fxy, that is x to the power 2 by 3 y to the power 1 by 3, where x is 2 and y is 1, I get the maximization in f as far as the constraint region, that is x plus y less than equal to 3 is concerned. This is Lagrange way, where lambda is called Lagrange multiplier. Then he went ahead and he calculated df by dc, means if x plus y less than equal to 3, I said if 3 is a constraint, that is c, instead of 3 I am saying c. C can increase, so line will shift. If c is a constraint, then what is df by dc? If I keep changing c, then how much the maximization in the function f is achieved? So df by dc equal to lambda. This is what he claimed. So this is then Lagrange came with the Lagrange function also, rather than fxy as a constant function. Fxy is a function over constant gxy. There are two functions. Can I mix these two as a single function called Lagrange function? So Lagrange function on based on x, y, z and lambda is nothing but fxy into lambda into gxy or some c. So he mixed fxy, gxy, lambda, c, everything, and he came up with a Lagrange function. Now, if you have Lagrange function where independent components are the variables and lambda, so if variable are x and y and lambda, then d Lagrange function by dx, d Lagrange function by dy, d Lagrange function by d, d lambda, if I calculate and equate it to 0, then immediately I get the value of x, y and lambda where the fxy, where the fxy set of xy where the fxy would be maximum. No need to do much more computation. This is what the ready-made solution Lagrange gave. But we came to different kind of solution. No need to have lambda and so many gradient vector. Nothing is required. What we saw in the concept that if I do dy by dx to calculate the extreme point, then extreme point, if I do dy by dx equal to 0, okay, if I have one independent component at x, so if x axis is this is y axis, and if I have a curve, then curve, if I do dy by dx and equate it to 0, and I get a value called x0. At x0 point, curve has maximum or minimum extreme point. At that point, if we see, if we draw a line, that line, if we take the x axis at that point, then x-axis becomes tangent at that point. This is what we saw. So dy by dx equal to 0. If I go with that and if I get a value x0, then at x0 where dy by dx is here, if I take the x0, y0 point on the curve, there if I shift the x-axis and touch the curve, then x-axis is parallel to the curve, is tangent to the curve at point x0, y0. This is what we saw. So dy dx equal to 0. To get a point, at that point x-axis is tangent. This is what we saw. Now here, if I have a curve fxy and point x0 y0 point, if the constant line is tangent, then if I do differentiation in terms of constraint line, this is patentable. So if I do differentiation with respect to the constraint line, here we did differentiation with the x-axis, and x-axis become tangent at the extreme point. Then if constraint line is becoming tangent at the extreme point in fxy, then I have to do differentiation with the constraint line. So if I have a function fxy and there is a constraint line gxy, then df by dg, dfx by dgxy. This is what we have to calculate. dfxy by dgxy. If gxy is a line, if I convert this line to a vector, then this becomes df by, if that vector is a g vector. Earlier it was a g line converted to g vector. Then df by dg is nothing but the directional derivative of a function along vector g. Earlier we have found that df by du, if I have a function f and then I calculate directional derivative along x-axis, we call it partial derivative. Directional derivative along y-axis means that is partial derivative along y-axis. Then directional derivative along any vector u, any unit vector u, is df by du. df by du. If I have df by dx, dfxy by dx, dfxy by dy, then certainly I can have dfxy by du, where u is any unit vector other than x-axis vector and y, I and j other than I and j. For that we saw it is nothing but the gradient vector of f multiplied by the u unit vector, dot product. So dot product of gradient vector f and the unit vector u. If I do dot product of these two, if I do the dot product of these two, then I get the directional derivative of function along vector u. So I am trying to now calculate df by dt, directional derivative of function f along g. Okay. Now that is gradient vector of f dot product the unit vector g. So fx into gx is the x component of the unit vector g, where fx is x component of the gradient vector of f. Fx into gx plus fy into gy. Now, if I want the extreme point, then df by dg should be 0. So whatever I am calculating now, fx into gx plus fy into gy, should I equate it to 0. Whatever comes, then that is the xy relationship I got. Now, if I go with this equation, fxy equal to x to the power 2 by 3, y to the power 1 by 3. Then gradient vector is 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3 j. This is the gradient vector where the vector for the gxy. So gxy is x plus y minus 3 equal to 0. So to calculate the for gxy, I am not calculating gradient vector. Gxy is a equation of a line. What would be the vector form of that line? This is what we are looking for. dfxy dfxy by dgxy is nothing but differentiation of function f along unit vector g. Unit vector g. G is a line now, so I have to convert g to a vector form. So if that is the case, then fx into gx, fx is the x component of gradient vector of f, where gx is the x component of the vector form of g algebraic equation. If I have algebraic equation x plus y minus 3 equal to 0, then vector form of this is nothing but you have to calculate the dy by dx. So dy by dx comes as minus 1. So the vector equation is I minus j. If x component is 1, then y component is minus 1, that is dy by dx. So I minus j is vector form of gxy. So dfxy by dg, that is the vector form, is nothing but x component of the gradient vector of f into x component of vector of g plus y component of the gradient vector of f into the y component of vector of g. Now x component of the vector of g is 1 and y component is minus 1. So net will become 2 by 3 into x to the power minus 1 by 3 y to the power minus 1 by 3 minus 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3 equal to 0. dfxy by dgxy equal to 0, so that I can get the extreme point. If that is the case, then we get 2 by 3 into x to the power minus 1 by 3 y to the power 1 by 3 equal to 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3. Now 3 I can cut down. Now if I take x, if I shift x on that side, y on this side, then it becomes 2y equal to x. Same thing. Quickly I get. No need to go for Lagrange multiplier and so many things. Quickly I get. Now anything I can calculate with this formulation. Now we took another example when fxy equal to x plus 1. X plus 1 is the x plus y. X plus y is fxy, where the constraint is x square plus y square equal to 2 square, that is 4. So there is a circle and circle parameter curve is the constraint. So I have to calculate maxima or minima only on the parameter, that is x square plus y square equal to 2 square, not less than equal to 2 square, not less than equal to 2 square. X square plus y square equal to 2 square. If that is the case, that is the constraint region, and the constraint region is the same, the parameter is only the constraint, and fxy equal to x plus y, gxy equal to x square plus y square equal to 2 square. Now in that constraint, I have to find the x and y set of x or y where fxy would attain maxima or minima. Now I have to calculate gradient vector for fxy, that is I plus j. df by dx, df by dy is 1, 1. So I plus j. Now gxy I have to convert it to vector form. So dy by dx I have to calculate. So y equal to now 4 minus x square square root. So dy by dx is equal to 1 by 2 into 2x minus 2x by square root of 4 minus x square. If that is the case, then dy by dx equal to minus x divided by a square root of 4 minus x square. Now I have to do df by dg, df by dg. G is now is a vector, that is fx into gx plus fy into gy equal to 0. So fx is 1, and now vector form what we are getting from x square plus y square equal to 2 square. The vector form is I minus x by square root of 2 square minus x square j. Now if I multiply with the gradient of f, then it becomes 1, 1, 1 minus x square, 1 minus x by square root of 4 minus x square equal to 0. So 1 equal to x by square root of 4 minus x square. So x equal to square root of 4 minus x square. So x square equal to 4 minus x square. So 2x square equal to 4. So x square equal to 2. If that is the case, then x equal to plus minus a square root of 2. Okay. If that is the case, now we have x square plus y square equal to 2 square. Then y square equal to 2. Then y is again plus minus 2. Now I have two extreme points here. One is plus minus 2 as x and plus minus 2 as y. So plus minus square root of 2 and plus minus square root of 2. So one point is a square root of 2 comma square root of 2 xy, and one point is minus a square root of 2 comma minus a square root of 2. Now these are the 2 points where fxy on the constraint gxy has extreme point. Now I can go ahead and place in x plus y, and we see that a square root of 2 comma square root of 2, it has maxima, and minus a square root of 2 and comma minus a square root of 2 is minimum. Quickly, now rather than going to Lagrange way where both gradient first you calculate, then equate with the delta, and then do all the computing. So this is something where we saw that when we are trying to, this is something called calculation of extrema or critical point with respect to any algebraic equation. Earlier we were calculating with the respect to x-axis and y-axis. Here with the respect to any algebraic equation, we convert algebraic equation to vector, and then it becomes a directional derivative along any vector. If converted, we will see more on the directional derivative. So this is the invention. This is the kind of that we will try to find patent on. So that is the idea. Anyway, we'll move ahead with the real life example. Real life example of of the maxima or minima can be kind of a square sum. So that is used in machine learning. So that is called a kind of a square word, a square distance. Okay, like I have set of points. This is x-axis and this is y-axis. If this is x-axis and this is y-axis, I have set of x, y points. Okay, now I have to draw a line where the vertical distance of all the points that is drawn on the line, that is squared distance. Vertical distance means vertical square of the vertical distance. Whatever the vertical distance, if I do square of it, then if I add all the vertical distances square, least square, it is called least sum of a square. So if I have all set of x1, y1, x2, y2, like that I have n point x and yn. Now I have to find an equation of line that is drawn inside the set of lines where if I see the vertical component of each point, that is y1, y2, y3, and then I draw a line from there that is perpendicular. Line is parallel to y-axis, and not perpendicular to the line I am drawing. If this is y-axis, this is x-axis, I am drawing a line passing through all set of points. Then all set of points I have to draw a line that is parallel to y-axis on that line. Then I have to calculate the square of the length of the line. If I add all the square, then it should be minimum. That line equation I have to find. Now, if I see the line equation, then equation of line is nothing but y equal to y0 plus mx, where m is the slope of the line, or dy by dx we also call. M is the slope of the line and y0 is the intersection in the y-axis. So, if there is any line y equal to mx, the line passes through origin. If I make an offset or intersection on the y-axis and intersection is at y0, then the equation of the line becomes y equal to y0 plus mx. Now, if I have any point x1, y1, then y1 is the vertical. Now, x1 is the horizontal. If it is x1, if I multiply with the m, then vertical become mx1. Then if I add offset y0, then the vertical, okay, so at x0, if I have x0, if I have a point, the point is x1, y1. Now, if I multiply, suppose the line that is passing, equation is y0 plus mx. So, if I multiply x1 with m, then it immediately gives me the vertical of, if, okay, so vertical of that point. If I add y0, then it becomes the line, it becomes the point on the line, that is the, if I draw the vertical from the x1, y1. Okay, if I have a point x1, y1, and from there I draw a line that touches the line I'm passing, and that line, then I have to find the length, the where it would intercept on the line. If I have a point x1, y1, from x1, y1 I draw a line and that is touching the wanted line, what we want, then that vertical distance, if I want to calculate, then if the equation of the line is y0 plus mx, y is equal to 0 equal to mx, then if I set as x1, then that interception point I can get as y0 plus m into x1. Now I have to decrease, I have to do subtraction, y0 plus mx1 minus the y1. Then that is the square distance. Now that I have to make square. Like that I keep doing for all the points. Now I have the square vertical distance of all the points that they are drawn on the line in terms of y0 and m. Otherwise, x1, all we have a scalar point. So x1 is a scalar. Only thing that is variable here is y0 and m. So the sum of a square distance from any point to a desired line. Now I got the full-fledged formula in terms of y0 and m. Now I have to find the minimization and maximization in terms of, I have to get the value of m and y0. Okay. Now I'll differentiate with m and I'll differentiate with y0, equate it to 0 to get the m and y0. Now you have got all the set of m and y0. Now check against the line equation that you have derived and at what it is minimum. Then you have found the global minimum. Now you have a line that is drawn in set of points where the square distance of that line in vertical direction to all the points, if you add that square distance, then it will come as minimum. So this is what that we can do as a professional. So this is the one example. Other example, that anyway we have seen fxy equal to x to the power 2 by 3, y to the power 1 by 3. Suppose that we have kind of production. So production is dependent upon two raw materials. This is a well-known example. So in my company, production is dependent upon two raw material. One has quantity as X and one has quantity as Y. So the production is has algebraic expression as x to the power 2 by 3 and y to the power 1 by 3. So it is more dependent on the quantity of x and less dependent upon the quantity of y. What quantity I can take for x and y so that production will be maximum. Now the constant is that x plus y should be less than equal. Constant is that net investment. So this is the production. This is the kind of production that we are seeing. Okay. Now the constant is that kind of the x plus y should be less than equal to some constant c. It is more on it, but we will hide now for the time. So consider that x and y I cannot take in input variable the raw material as infinite because production will be higher. They have constant that x plus y is less than some c. Now, for example, I take c equal to 3, then quickly I find the value of x and y where the maximum f can have. Now, we can replace 3 with any c, and in terms of c, now I can find that f how in terms of c and x and y it would reach the maximum. So production in the company based upon the input material X and Y, how it can reach maximum that we can see through the calculation. Okay, so this is something that we can do as far as calculating the profitability in the company is concerned, or the least square distance. Means whatever you want, you bring in algebraic equation and have well-defined input variable. Derive with the input variable like x and y separately, set it to 0 and get the value of x and y on which your algebraic equation is minima or maxima. What you want? You want maxima or minima? Select those. If you want minimum, then select all the minima and get the global minima. If you have constraint, then go with the hour formula. This is what I would say, and quickly you maximize the profit of your company. So what else you want? So this is the most professional reason in the calculus, that is the maximizing the profitability of the company through maxima or minima. Okay, so we will conclude this maxima and minima. Now we will see a kind of revisiting the directional derivative of any function along a particular vector. Then we will go into kind of much enjoyment called line integral, flux integral, okay, and this curl integral, this kind of more professional way where we have vectors now. Vector calculus is more prominent now. Earlier we had algebraic calculus, little bit we saw in the vector calculus, but only the concept wise. Now in professionalism, how we can use vector calculus, where at each point in algebra has a point. Now each point in algebra is a vector. So those things that we'll see later on. Let's keep enjoying.